welcome back. I'm going to jump into example 1. Example 1 is going to be one giant example from part A all the way up to part R. We have a table here. This table represents people from these 3 cities and their favorite mode of transportation. Part A. If one person is selected, find the probability that the person prefers travel by plane. In symbols, what I'm looking for here is probability of plane. So I'm picking one person, but the bottom number here is going to be how many possible people could I have picked. That's just going to be the total number of people I have in my table. So add up all these numbers. 6 plus 15 plus 12, plus 5 plus 9 plus 10, plus 0 plus 6 plus 17. And that's 80. So there's 80 people represented by my table. And that's going to be my bottom number. For the top number, how many people prefer plane? That's going to be 12, 10, 17. So 12 plus 10 plus 17 is 39. Part B, if one person is selected, find the probability that the person is from Los Angeles and prefers travel by plane. Keyword here is the word and. In symbols, we're looking for probability of Los Angeles, LA, and plane. The bottom number is going to be everybody, that's 80. And then remember, in probabilities, the word and means I want people who satisfy both of these requirements at the same time. Okay, so how many people are from LA and at the same time prefer travel by plane? And as a hint, for ands, it should be a single box. So which box represents LA plane? LA plane, 17. Part C, if one person is selected, find the probability that the person is from San Francisco or prefers travel by train. Keyword here is the word or. In symbols, we're looking for probability of San Francisco, so SF, or train. Bottom number is going to be everybody, which is still 80. And then remember, in probability, the word or means I want people who satisfy at least one of these requirements. So they don't have to satisfy both. They only have to satisfy one or more of these requirements. And the way we did it in the last lecture was I'm going to start by taking all my San Francisco numbers, which is 5, 9, and 10. So definitely these people satisfy the first requirement. So 5 plus 9 plus 10. And then I'm also going to throw in the train numbers, which is 15, 9, and 6, because these people would satisfy the second requirement. Now keep in mind that I don't want to count the 9 twice. The 9 I already counted when I counted my San Francisco numbers, so I just need to add on the 15 and the 6. Bottom's 80, up top, 5 plus 9 plus 10 plus 15 plus 6, and that's 45. Part D, if one person is selected, find a probability that the person's favorite mode of transportation is not by car. In symbols, we're looking for probability of not car. Bottom still going to be everybody, which is 80. And then for the top, I want not car. So not car numbers would be the train numbers and the plane numbers together. So 15 plus 9 plus 6. And then plus 12 plus 10 plus 17. And that's 69. So parts A through D here on the front page, this is just review from the last lecture. And then for this lecture, we're going to add on to this. The first new thing we're going to talk about in this lecture is conditional probability. That's the symbol for it. Let me explain to you what that means. The way you read the symbol is probability of A the line stands for the word given, that B already occurred. Okay, so the word given, it's kind of the key word here, and that's represented by this line. Okay, so another way to think about this is probability of A given additional information. That's represented by B. Okay, so let's try some examples. Part E. If one person is selected, find a probability that the person prefers travel by car, given that the person is from San Francisco. Keyword here is the word given. So in symbols, what I'm looking for here is probability of car, given, that's represented by the line. So car, given, San Francisco. Anytime you have the word given, the bottom is not going to be everybody. So the bottom is not going to be the total 80 here. So because we're given additional information that this person is from San Francisco, right? So I know for sure that this person is from San Francisco. So from my table, I should only focus just on the San Francisco numbers, right? I should ignore everything else and just focus on the San Francisco numbers because I know for sure that this person is from San Francisco. So the given part is really telling you what part of the table you should restrict yourself to or what part of the table you should focus on. So this is telling me I should focus just on these San Francisco numbers. For the top and the bottom. Okay, so focusing just on the San Francisco numbers, how many are there total? So just the San Francisco numbers, 5, 9, 10. The total would be 24. And then still focusing just on the San Francisco numbers, for the top, how many are car? So focusing still on the San Francisco numbers, how many are car? 5. Let's do another example. Part F. If one person is selected, find a probability that the person is from San Francisco, given that the person prefers travel by car. Once again, keyword here is the word given. In symbols, what I'm looking for here is probability San Francisco, given, that's the line, car. Okay, once again, the given part is telling you what you should focus on, and that's the second part. Right? The second part here is car. That's telling me I should focus just on the car numbers and ignore everything else in the table for the top and the bottom. Okay, so just focusing on car numbers, how many are there total? Just car numbers, 650. Total here is 11. And then still focusing just on the car numbers, how many are San Francisco? So just car numbers, how many are San Francisco? Just car numbers, how many are San Francisco? 5. All right, so let's pause here a bit. Notice that in part E, it's car given San Francisco. In part F, it's San Francisco given car. So the only difference here is the order. And notice that you do get two different answers. So the point I'm trying to make here is that for given problems, for conditional probability problems, the order does matter, right? So car given San Francisco gets you a different answer than San Francisco given car. All right, so let's do one more example. Part G, if one person is selected, find a probability that the person is from Los Angeles, given that the person prefers travel by train. So in symbols here, I'm looking for probability Los Angeles, given train. Now, which numbers should I focus on? The LA numbers or the train numbers? Which one? It's always the given part, and the given part is always the second part. So this is telling me I should focus just on the train numbers. So we're going to focus just on the train numbers. For the top and the bottom. And focusing just on the train numbers, how many are there total? Train numbers will be 1596. Total here is, I think, 30. 1596 total is 30. And then still focusing on the train numbers, for the top, how many are LA? So just on the train numbers, how many are LA? 6. In the last lecture, we talked about an addition rule. And the addition rule was a formula for finding ORs, and it's called an addition rule because of this plus sign. Today we're going to talk about the multiplication rule. And so a multiplication rule is going to be a formula for finding ands. And let me point out that we already know how to find ands without using a formula at all. In part B on the front page, we already did LA and plane without using a formula at all. So this formula is not going to be useful for questions that have a table. Okay, but let me explain where the formula comes from. LA and plane means I'm looking for people that satisfy both requirements at the same time, right? So if you have a table, it's easy to find exactly who those people are, right? So it's these 17 people. These are 17 people who are from LA and at the same time they like plane. But if we didn't have a table, what's another way that we can get those same people? So you can do it in steps, right? You can start off by picking people from LA. That's step 1. And then picking the plane people from that group of people from LA. So after that 2-step process, you're going to have a person who is from LA and at the same time likes planes. So that's the basis of the formula. So the formula says to find probability of A and B, so probability of LA and plane, we're going to first pick people from LA. That's represented by probability of A. And then you're going to pick the plane people. But not any plane people, right? I don't want just any plane people. I want the plane people from that group of LA people that I just picked. So it's not going to be regular probability of B. It's going to be probability of B given that I already picked the LA group. Okay, so probability of LA, and then probability of plane, but not any plane, plane given that I already picked the LA group. So plane from that group of LA people that I just picked. Okay, so we're going to use this formula for the examples on this page. Notice that the examples on this page, it says if 2 people are selected, if 3 people are selected. So this differs from everything on the first 2 pages because everything on the first 2 pages were all if 1 person is selected. Okay, so we're going to use the idea of the multiplication rule to handle picking multiple people. And the first idea is to handle 2 people. We're going to do it in 2 steps. Right, we're going to pick the first person, and then we're going to pick the second person. All right, so let's jump in. Part H. If 2 people are randomly selected, what's the probability that the first person prefers travel by plane and the second person prefers travel by plane? All right, so we're going to start off with the first person. So what's the probability that the first person prefers travel by plane? The bottom is going to be everybody. And so how much is everybody? Everybody is 80. And then let me make a note to myself. The first person I want to prefer plane. And so how many people like plane? 12, 10, 17. So 12, 10, 17 I think is 39. And that takes care of the first person. And then the second person also prefers travel by plane. So that's going to be another fraction. And this person, I also want to be a plane person. Okay, and this is where the second idea comes in. So this B given A. So when I make the second fraction, I have to keep in mind that I already picked 1 person in this first slot already. Okay, so for the second fraction, because I already picked 1 person, I don't have the full 80 people anymore. Right? I should be down by 1 person. So I should be down to 79 people now. And then for the top, I want a plain person. So plain person would be 12, 10, 17, which is 39. But once again, keep in mind that I already have this first person who was also a plain person. So I don't have the full 39 here. I should be down to 38. Now let's do another example. If two people are randomly selected, okay, so because it's two people, I'm going to end up with two fractions. And actually, these fractions are multiplied together. On the lab, you don't have to multiply them together, just leave them as fractions with a multiplication sign in between. I should just leave it exactly like this. All right, so if two people random selected, what's the probability that the first person is a person from Los Angeles who prefers travel by train? So first person is LA train. And the second person is from San Francisco. So second person, San Francisco. All right, we're going to handle this as two separate fractions in steps. For the first person, the bottom's going to be everybody, so it's going to be still 80. And then for the top, I want LA train. So how many people are LA train? 6. Okay, and then now for the second fraction, keep in mind that we already picked one person already. So for the bottom, we should be down to 79 people. For the top, I want San Francisco people. San Francisco would be 5, 9, 10. 5, 9, 10 together is 24. So what do I put here? Do I put 24? Or did I have to reduce it by 1 like I did in part H? So the question you should ask yourself is, have you used any San Francisco numbers yet? You haven't, right? The first person was LA, so you haven't used any San Francisco numbers yet. So you should still have the full 24 here. In part H, we had to reduce by 1 because the question was, did we use any plain numbers yet? And the answer there was yes. The first person was a plain, so I did have to reduce it by 1 for the second fraction in part H. Next, J. If 3 people are randomly selected, okay, so this is now 3 people, which means I should have 3 fractions. What's the probability that the first person is a person from San Francisco who prefers travel by plane? So first person is SF plane. The second person is a person from Los Angeles who prefers travel by plane. Second person is LA plane. And the third person prefers travel by plane. So third person is plane. And it doesn't say in the city, so just any plane. First fraction, the bottom's going to be everybody, so that's 80. And then for the top, I want SF plane. So SF plane is 10. For the second fraction, right, for the bottom, keep in mind that we already picked one person already. So we're actually down to 79 for the second fraction. For the top, I want LA plane. LA plane would be 17. Okay, and here's where you think. So have I used any LA plane yet? I have not, right? I used SF plane, but I haven't used any LA plane yet, which means I should still have the full, 17. So this, you don't reduce by 1, so we're still at 17 here. For the third fraction, right, for the bottom, I have one person already, I have 2 persons, so I actually should be down by 2. So for the third fraction, we should be down to 78 now, total people. For the top, plane. So plane would be 12, 10, 17. So 12, 10, 17 is 39. What do I put here? And the question you should ask yourself is, have you used any plane numbers yet? Yes, you have, right? First person is a plane, second person is plane. So you've actually used 2 plane numbers. which means for this last one, you need to reduce it by 2. Right? So it's not going to be the full 39. It's going to be 39 minus 2, which is 37. Okay, so make sure you understand why this is 37 and not 39. Okay, part K. If 3 people are randomly selected, so I need 3 fractions here. What's the probability that the first person is a person from Sacramento who prefers travel by car? So first person is Sacramento car. Second person is a person from Los Angeles who prefers travel by train. So second person is LA train. Third person prefers travel by car. So car, no city specified, so any car. First fraction. First fraction, bottom should be everybody, so that's 80. And then I want for the top, Sacramento car. Sacramento car, 6. Okay. Second fraction, keeping in mind that you already picked one person, which means we're down to 79 on the bottom. For the top, I want LA train. LA train is 6. Okay, and the question is it 6 or is it 5 or is it 4? Question you should ask yourself is, have you used any LA train yet? No, right? The first person was Sac car, so we haven't used any LA train yet. So you should still have the full number here, which was 6. And I kind of picked bad numbers here. So this 6, the first 6 was 6 from the Sac car. The second 6 is the 6 from the LA train, right? They had nothing to do with each other. Third fraction. Third fraction, keeping in mind we already picked 2 people, so we should be down to 78 on the bottom. And then up top, car. So car is 650, so that's 11. Question you should ask yourself is, have you used any cars yet? Yes. The first person was car. So you used 1 car already, which means I should be down to, I should be down by 1. So it's not going to be the full 11, it's going to be down to 10. Okay, so make sure you understand why this is 10 and not 11. And make sure you understand why in part J, we had to reduce by 2, whereas in part K, we reduced by 1. Right? In part J, we used 2 planes in the first slot and the second slot, so I had to reduce it by 2. In part K, I only used 1 car in the first slot, so I only have to reduce by 1. In the last lecture, we talked about complements. What's the complement? Think of the word not. Right? So if E means it rains today, then the complement of E means it does not rain today. And what's the relationship between the two? If you know that the probability of it raining today is 0.30, then the probability of it not raining today, you can just do 1 minus 0.30. So to find the probability of an event, you can go 1 minus the probability of its complement. And that's going to be the strategy that we're going to use right now. So why do we need this strategy here? Let's read part L. So part L says, if 3 people are randomly selected, find a probability that at least 1 person is from Sacramento. So key word I see here is the word at least 1. What does at least 1 mean? At least 1 means 1 or more, right? So if we're talking about 3 people, it could mean 1 person is from Sacramento, it could mean 2, it could mean 3 people are from Sacramento. And it's actually even worse than that, because when I say 1 person is from Sacramento, there's actually many possibilities there, right? It could mean the first person is from Sacramento and the other 2 are not. It could mean the second person is from Sacramento and the other 2 are not. It could mean the last person is from Sacramento and the other 2 are not. So that's 3 possibilities right there. For 2 people, it could mean the first 2 are from Sacramento and the last person is not. It could mean the last 2 are from Sacramento and the first person is not. It could mean the first and last people from Sacramento and the middle person is not. So that's another 3 possibilities. So we're at 6 possibilities now. And then for 3 people from Sacramento, I think there's only one way, right? All 3 from Sacramento. So in total, if you're going to do at least one directly, you would have to calculate 7 probabilities, right, for each of those cases. So the idea here is sometimes instead of doing things directly, it's easier to find a complement and then do 1 minus that answer. So that's going to be a strategy we do right now. So what is the complement of at least 1? So what is not at least 1? So let me write out some numbers here. Which of those numbers would qualify as at least 1? Well, at least 1 means 1 or more, right? So that counts, that counts, that counts, that counts, that counts, that counts. So all of those numbers count as at least 1. So which of those numbers is not at least 1? 0, right? So the complement of at least 1 is 0 or none. So I'm going to write none here. So the idea here is to find a probability of at least 1. Instead of doing it directly, we're going to do 1 minus the complement, which is the probability of none. Because that's going to be easier. There's only one situation for none, right? It's just 0. So part L. So we're looking for 3 people and at least 1 from Sacramento. So probability of at least 1 . So at least 1 Sacramento should be the same thing as doing 1 minus the probability of none from Sac. Okay, so the idea here is I'm going to find a probability that nobody is from Sacramento and then just do 1 minus that. All right. So if I have 3 people, we're going to find a probability that none of them are from Sacramento. Okay, we're talking about 3 people, which means I need 3 fractions. Okay, and 3 people, none of them from Sacramento means that the first person is not Sac, the second person is not Sac, and the third person is not Sac. Right? That's what it means for 3 people, none of them being from Sacramento. So it means not Sacramento, not Sac, not Sac. Okay, and so we're just going to find the fractions for not Sac, not Sac, not Sac. So the bottom, it's going to be everybody, and I think everybody is 80 for this table, right? 80. And then how many people are not Sacramento? So not Sacramento would be the last 2 rows. So 5, 9, 10. So 5 plus 9 plus 10 plus 0 plus 6 plus 17. And it's 47. So 47 people not from Sacramento. Okay, so that takes care of the first person. Probably that the second person is not from Sacramento, right? So remember, keep in mind that you already have a not Sac person in the first slot. So for the second slot, we're down to 79 people. And then how many people not from Sacramento? Right, keeping in mind the first person is not Sac. So the second person, I have to reduce that by 1. So we're now down to 46. For the third person, right, the bottom number, we're down to 78. And then for the top, I want another not Sac, right? I already have 2 not Sac people, which means I need to reduce it again. So we're down to 45. Right, so your answer here would be 1 minus 47 over 80 times 46 over 79 times 45 over 78. Part M. If 3 people are randomly selected, find a probability that at least 1 person prefers travel by train. Right, keyword I see here is at least 1. Right, anytime I see at least 1, I'm going to set it up as 1 minus none. right? So probability at least one, I want at least one train. We're going to set that up as 1 minus the probability of none train. All right, so this is going to be 1 minus. We're talking about 3 people. All right, so 3 people would mean 3 fractions. And then 3 people, none of them like can train, means not train, not train, not train. Right, so all 3 I want to be not train. For the first fraction, the bottom's going to be everybody. Everybody, I think, is 80. And then how many not trained people? Not trained would be the cars and the planes. So 6 plus 5 plus 0. 12, 10, 17. 12, 10, 17. So that's 50. Second fraction, the bottom, we should be down by 1 to 79. And then for the top, I want another not train, so I need to reduce it by 1. So we're down to 49 for the top, for the second fraction. For the third fraction, the bottom, we're down by 1 again, so we're down to 78. And then for the top, I want another not train, so we actually have to reduce it again by 1. So now we're down to 48. And that's our answer. Part N. If 3 people are randomly selected, find a probability that all 3 prefer travel by plane. Okay, notice that. Do you see at least one anywhere in that sentence? No, right? So I don't see at least one, so you're not going to set this up as 1 minus none. This one, if it doesn't have at least one, this will be the same as on the previous page. So you can just do this one directly. 3 people means 3 fractions. And I want all 3 to prefer train or plane. So all 3 here will be plane. And then you can do this the same way that you did it on the previous page. So first person, plane. Bottom's going to be everybody, so that's 80. Plane, 12, 10, 17. I think that's 39. Okay, second person, for the total at the bottom, we're down by 1 to 79. Plane, so we used 1 plane already. So actually we should now be down to 38. For the third person, the bottom, we're down by 1 again, so now we're down to 78. And then for the top, I want another plane person, so that means I should be down by 1 again. So we're down to 37 here. Okay, notice that there's not a 1 minus, right? Because this is not a at least one problem, which means you're not going to set it up as 1 minus none. We talked about mutually exclusive in the last lecture, but let me remind you what it is because we'll need it on the next page. So 2 events, A and B, are mutually exclusive if they cannot both happen at the same time. And then we also talked about a math definition that you check. Okay, and the math definition you check is you check the and. Okay, so this is the probability of A and B both happening at the same time, right? If they cannot happen at the same time, the probability is going to be 0. So you check the and. If it's 0, it's mutually exclusive. If it's not 0, it's not mutually exclusive. And then the new terminology in this section is independent. So 2 events, A and B, are independent. if they don't affect each other. If the occurrence of one does not affect the occurrence of the other. Then we also have a math definition to check. And before I get to the math definition, let's actually talk about some examples first. Okay, so for each pair of events, we're going to decide whether they are independent or dependent. Dependent is the same thing as not independent. I'm going to use the words not independent instead of dependent. First one, flipping a coin, rolling a die. Here's a coin. Here's a die. So if I flip a coin, does what happens when I flip a coin affect what happens when I roll this dice? No, it doesn't, right? So who cares? This dice doesn't care what happens with the coin, right? So they don't affect each other at all. So if they don't affect each other at all, then it's going to be independent. Next one, being kind and having many friends. Does being kind affect whether or not you have many friends? It probably does, right? So if it does affect, then it's going to be not independent. It's going to be not independent. Next one, drawing a card from a deck and getting a queen, not replacing, and then drawing a second card. Right, so here I have a deck of cards. If I draw a card and I get a queen, and if I don't put it back, does it affect what could happen next? Does it affect whether or not I get a queen on the next draw? Yes, it does, right? So if I don't put it back, then I actually have one less queen now, right? So there's 4 queens in the deck. If I take this one and I don't put it back, then there's actually now 3 queens, and so it reduces my chance of getting another queen. So taking a card and then not putting it back does affect what happens on the second draw. So if it does affect, then this will be not independent. Next one, drawing a card from a deck of cards, getting a queen, replacing it, shuffling, and then drawing a second card and getting a queen. So this one, I'm drawing a card, getting a queen, I'm putting it back, shuffling, and then I'm drawing a second card. So putting it back and reshuffling just resets the situation, right? So whether or not I get a queen on that first draw, because I'm putting it back and I'm reshuffling, right, it resets the situation and it doesn't affect whether or not I get a second queen on the second draw. So putting it back and reshuffling is going to make this independent. And then for us, these are going to be two important examples. So for us, we're going to be sampling people, right? So if I pick a person and I don't put them back and I pick a second person, right, that's going to be picking a card, not putting it back. So that's called sampling without replacement. So sampling without replacement is going to be not independent. Drawing a card, putting it back, so that's picking a person, putting them back so that you can actually possibly pick them again. That's called sampling with replacement. Right, and sampling with replacement is going to be independent. And then the last example, studying hard and getting good grades. So does studying hard affect whether or not you get good grades? It probably does, right? So if it does affect, this is going to be not independent. Okay, so now let's go back and let me tell you the math definition that you need to check. So I'm going to write one down and then I'll explain it. So for independent, you're going to check probability of A equals probability of A given B. So where does this equation come from? So this means probability of A given that B already occurred. Okay, so what this is saying that probability of B, knowing that B already occurred, gives you the same answer as regular probability of A. In other words, sticking on this given B doesn't change the answer, right? That's exactly what it means for B not affecting A at all, right? Knowing that B occurred, you get the same answer as regular probability of A, okay? So that's one equation you're going to check. And there's two other equations that you could check. You don't have to check them all. You just check one of them. I'm always going to check this one, but let me write the other two just to be complete. So the second one you could check is going to be the same thing as this one, except you just swap B's and A's. So this one's going to be probability of B equals probability of B given A. Okay, and then or. The third one you could check. I almost don't even want to write this one, but I'll write it anyway. So the third one you could check is probability of A and B equals probability of A times probability of B. This last one comes from the multiplication rule that we just talked about earlier. So the multiplication rule says probability A and B equals probability of A, right? Probability A and B equals probability of A times probability of B given A. Now, if I know B and A are independent, then I know the probability of B given A is the same thing as regular probability of B. So if I know that A and B are independent, I can replace probability of B given A with regular probability of B. And you'll get exactly this. Okay? So the reason why I don't like writing this one is because I've seen a lot of people confuse this with the multiplication rule. So this last one, I'm going to write a warning here. You should only use the last one if you know A and B are independent. Or if you are checking independent. Okay, so you're only going to use equation 3 if you know ahead of time that A and B are independent, or if you're checking whether A and B are independent. Okay, in any other case, you should be using the regular multiplication rule, which has this B given A instead of regular B. Okay, which is why I'm never going to use the third one. I'm always going to check this first one. All right, let's see how we can use those math definitions to check whether two things are independent or mutually exclusive. Part O, let A be the event that the person is from Sacramento, let B be the event that the person prefers travel by plane. Are A and B independent? Right. I'm asking about independent. So which equation should we be checking? You're either going to check this one, right? This is for mutually exclusive. For independent, you're checking this one, right? Or 2 or 3. I'm always going to pick the first one. All right, we're checking independent. So I'm going to check P of A equals P of A given B. So let me write that down. And A and B mean something in this example. So A meant Sacramento. So this is probability of Sacramento equals probability of Sacramento given, and B meant plane. And what we're going to do here is just check the left side and check the right side. Right? Left side, probability of getting someone from Sacramento. And we're going to find the probabilities from the table again. So probably Sacramento, the bottom's going to be everybody. So everybody was 80. For the top, I want the people from Sacramento. So how many people from Sacramento? Sacramento would be 6, 15, 12. So 6, 15, 12 would be 33. Right, that's the left side. The right side, we're going to calculate SAC given plane. Right, so this is a conditional probability. SAC given plane means that we're focusing on something. What are we focusing on? SAC or plane? Which one? It's always the second one. So we should be focusing on the plane numbers. For the top and the bottom. Okay, so focusing just on the plane numbers, how many are there total? So just the plane numbers would be 12, 10, 17. So 12, 10, 17 total would be 39. And then still focusing on just the plane numbers, how many are from Sacramento? So just the plane numbers, how many are from Sacramento? 12. Okay, and the question is, are these two things the same or not? And so they're fractions right now. It's hard to tell whether they are the same or not. So just divide. So 33 divided by 80. And I'll round to 3 decimal places here. 0.413. 12 divided by 39 is 0.308. Okay, are they the same or not? They're not, right? So if they're not the same, then it's not independent. Okay, so for the labs, you're going to type in the left side and the right side, and then don't type in the decimal. The decimal you'll check on your own to come up with the conclusion. Part P, let A be the event that the person prefers travel by car. Let B be the event that the person is from Los Angeles. Are A and B mutually exclusive? Right, so for mutually exclusive, I should be checking this equation. Right, so we're checking P of A and B equals 0. Right, in this case, A and B meant something. So A meant car, and B meant LA. Okay, we're going to check left side, check right side. Right side's easy. Right side's actually just 0. That's the easy part. Left side, probability of car and LA. So car and LA. So if I don't see the word given, if I don't have like this given probability, then I know the bottom is going to be everybody. Everybody was 80. And then for the top, how many people are car and LA? So at the same time. So car and LA would be 0. Okay, left side 0 over 80, right side 0. Are they the same or not? They are the same, right? So 0 divided by 80 is actually just 0. So they are the same, they are equal. So if they are equal, then it is mutually exclusive. Q. Let A be the event that the person prefers travel by train. Let B be the event that the person is from San Francisco. Are A and B independent? So which equation should I be checking? Independent, I'm checking this one. Probability of A equals probability of A given B. And then I'm going to replace A and B with what it means in this case. A meant train. B meant San Francisco. Okay, and then we're going to calculate left side, right side separately. Left side is just probably a regular train. I don't see given, so the bottom is going to be everybody here, which is 80. And then how many trains do I have? Train would be 1596. 1596, I think it's 30. Okay, that's the left side. Right side, train given SF. So anytime I have this given, the bottom is not going to be everybody anymore. The bottom is, we have to focus on what numbers here. I should be focusing on the given part, which is the second part, which is SF. So I should be focusing on just the SF numbers for the top and the bottom. So just on the San Francisco numbers, how many are there total? So just San Francisco, 5, 9, 10. The total is 24. And then still focusing on just the San Francisco numbers, how many are train for the top? So just the San Francisco numbers, how many are train? 9. Okay, so left side 30 over 80, right side 9 over 24. Question is, are they equal? All right, so right now, there are two fractions with different denominators, so it's hard to tell. Divide. So 30 divided by 80, 0.375. Right side, 9 over 24. 0.375. So they are equal. So if they are equal, then they are independent. Or let A be the event that the person is from San Francisco. Let B be the event that the person prefers travel by plane. Or A and B mutually exclusive. All right, so mutually exclusive. Which equation should I be checking? We should be checking this one. So probably A and B equals 0. So we should be checking okay, A here meant San Francisco, so we're looking for probability of San Francisco. B meant plane. Okay, check left side, check right side. Right side's easy, it's just 0. Left side, we have to calculate probability San Francisco and plane. I don't see the given, so this is going to be, the bottom's going to be everybody, so it's going to be 80. And the top, I want San Francisco and plane. So, and remember, should refer to just a single box. San Francisco plane, 10. Okay, question is is left side equal to the right side? You can check on your calculator if you want, but definitely 10 over 80 is not equal to 0. So if they're not equal, then it's not mutually exclusive. All right, we just finished example 1, which was one giant example involving a table. So now we're going to talk about some examples that don't have a table. So we'll have to rely on formulas. Let me remind you what the formulas are. So the first one is the addition rule, which was a formula for finding ORs. And it says the probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. This is a formula from the previous lecture. And then today, the new formula we talked about was the multiplication rule, and it's a formula for finding ands. And it says probability of A and B is the probability of A times the probability of not just regular B, but probability of B given A. Remember, for the conditional probability, the ones that have the given, the order does matter. So make sure it's A and then B given A. And then there's a third one, which is going to be useful for us. And you get that third one by swapping the A's and B's. So probability of B and A is equal to the probability of B times the probability of A given B. Right, so all I did was I started with equation 2 here and just swapped the A's and B's, right, and I got 3. So this is going to be useful because for ors and ands, the order doesn't matter, right? So A or B is the same thing as B or A. A and B is the same thing as B and A. So the left side here is the same, okay? The right side is different, right? The right side of the first one involves a B given A. The right side of the third one involves an A given B, and these are different. So it's going to be useful because sometimes you'll have A given B, and sometimes you'll have B given A given in the problem. So that's going to determine which of these formulas you use. And then the rule of complements. So this is just a relationship between an event and its complement. And it says the probability of the complement is 1 minus the probability of the original. And the probability of the original is 1 minus the probability of the complement. Example 2. Suppose that the probability of G is 0.45, probability of H is 0.15, probability of G given H is 0.70. Find the following quantities. I don't have a table, so I have to rely on those formulas on the previous page. So what I'm going to do here is, these formulas are written with A's and B's. This equation, or this problem, is asking about G and H's. So I'm going to rewrite the formulas using G and H. So the first one is the addition rule. So I'm just going to replace A with G and B with H. So this is going to say probability of G or H equals probability of G plus probability of H minus the probability of G and H. The second equation is the multiplication rule, which is the one for ands. So it's a probability of G times probability of, make sure you have the correct order here. Is it G given H or is it H given G? It's H given G. So one way that I remember is, I know that it alternates, right? So G, H, G. And then the third one, you get by starting with 2 and then just swapping the letters. So this will say probability of H and G is equal to the probability of H times the probability of, once again, it should alternate. So it's H and then G given H. All right, so now we're ready to answer these questions. Part A, find the probability of G and H. So which equation should I use? So look for the equation that has a G and H in it. So equation 1, I see it right here. Equation 2, I see it right here. Equation 3, so this is in the wrong order, H and G, but remember I said for ands, the order doesn't matter. So this is actually the same thing as G and H. So I see it in equation 3 also. Okay, so it's in all 3 equations. Which one do you use? Can you use equation 1? I'm looking for G and H, which is right here. So for this equation to be useful, you need to know everything else. Okay, so do I know probability of G? Yes. Do I know probability of H? Yes. Do I know G or H? No, right? So I don't know G or H, which means equation 1 is not going to be useful to me. Okay, what about equation 2? G and H is right here. So for this one to be useful, I need to know everything else. So probability of G. Do I know probability of G? Yes. Do I know H given G? I know G given H, but remember for the givens, the order matters. So these two are different, so I don't know H given G, which means I can't use equation 2. So the only one left is equation 3, right? So this is what I'm looking for. I know probability of H, and I know G and H, or G given H. So equation 3 should be useful to me. So let me write it out. Let me recopy equation 3. So it says H and G is equal to probability of H times the probability of G given H. And then now we just fill in stuff. H and G is what I'm looking for. So let's just call that X. Probability of H is 0.15, so this entire thing is 0.15. Probability of G given H is 0.70. And then I'm going to go through and fill in the symbols. So there's an equal sign right here. There's a multiplication sign right here. And then your job is to get the X by itself. The X is already by itself, so all you need to do is just multiply on the right side. 0.15 times 0.70, and it's 0.105. Okay, so what we just found was probability of G in H is 0.105. Part B, probability of G or H. So which equation is going to be useful? There's only one that has an or in it. It's equation 1. Right, so there you have no choice but to use equation 1. So let me recopy equation 1. And then we'll go through and fill in what we know. So G or H, that's what we're looking for. So let me just call that X. Probability of G is 0.45. Probability of H is 0.15. Probability of G and H, do I know that? I do, right? We did that in part A, right? So probability of G and H is 0.105. And then go through and fill in the symbols. So there's an equal sign right here. Be careful. There's a plus sign in the middle here. And then between these two, there's a minus sign. And then your job is to get the X by itself. The X is already by itself. So all you need to do is simplify the right side. So right side is going to be 0.45 plus 0.15 minus 0.105. And you get 0.495. All right, so we just found G or H. So probability of G or H is 0.495. Part C, probability of H given G. Okay, which equation has H given G? Okay, remember for the givens, the order does matter, so you need to see exactly in that order H given G. Which equation has a H given G? I see it right here, and that's the only place. So you have no choice but to use equation 2. Okay, so let me recopy. And then go through and fill in what you know. Left side, G and H. Right, so if you're paying attention, we actually already know that. We did that in part A, right? G and H is 0.105. So I know this entire thing is 0.105. G was in the original problem. It's 0.45. h given g, that's what we're looking for. So let me call that x. And then we'll go through and fill in the symbols. So there's an equal sign here. There's a multiplication between those two, the 0.45 and x. And then your job is to get the x by itself. Okay, so here the x is not by itself right now, right? There's this 0.45 being multiplied. So to get rid of the 0.45, you're going to do the opposite of multiplication. So divide both sides by 0.45. Okay, left side, 0.105 divided by 0.45. Rounded to 3 decimal places is 0.233. And then on the right side, 0.45 divided by 0.45, those cancel out, and you just have an x, and you're done. So what we just found was probability of h given g is 0.233. Part D. Are G and H independent? Okay, so let's go back and look at our notes. Independent. The question is, which equation should you check? You really have two choices: this one or this one. So which one? Independent, you should be checking this one. So probability of A equals, and make sure you have the correct order, so it's A equals A given B. And then because this question involves G's and H's, let me replace the A's with G's and the B's with H's. Okay, so what we're really checking is probability of G and then probability of G given H. And then you're just going to find the left side and find the right side. So left side, probability of G, we know is 0.45. G given H, that's not it, that's the wrong order. G given H, 0.70. Okay. If they're equal to each other, they're independent. If they're not equal, they're not independent. Obviously, these are not equal. So our conclusion here is that they are not independent. Part E, let G and H are G and H mutually exclusive. Right, mutually exclusive. You're checking the and, right? P of A and B is equal to 0. And then because we're talking about G and H's here, let me rewrite probability of G and H is 0. And then check left side, check right side. Right side's easy, it's just 0. Left side, probability of G and H. We probably did that already somewhere. Where do I have G and H? Right there. So G and H is 0.105. Okay, question is, are they equal to each other or not? If they are, then it's mutually exclusive. If they're not equal to each other, then it's not mutually exclusive. So obviously, this would be not mutually exclusive. Example 3. Let C and D be events such that P of C is 0.8, probability of D is 0.6, and probability of C or D is 0.92. We don't have a table, so I need to rely on those 3 formulas. Let me rewrite them here. And I'm going to rewrite them using C's and D's. So instead of the A's and B's in the original, I'm going to rewrite them with C's and D's. The first one is the addition rule, which is the one for OR. So C or D is equal to probability of C plus probability of D minus the probability of C and D. The second one is the multiplication rule. This is the one for ands. So C and D equals probability of C times, and then the correct order here, it alternates. So it's C and then D given C. And then the third one, you get by just swapping the order of equation 2. So that's going to say probability of D and C equals probability of D times the probability of, it alternates here, so it's D and then C given D. Okay, we're ready for part A. Part A says, are C and D mutually exclusive? Okay, so I see mutually exclusive. That means I should be checking some equation. Which equation should I be checking? The and. Okay, so I'm going to write this using C's and D's. So I'm looking for probability of C and D is equal to 0. All right, so we're going to check C and D equal to 0. Okay, I'm going to find the left side, find the right side, and then see if they're equal or not. Right side's easy, it's 0. Left side, I don't know right now, so I actually have to find it. And we're going to find it using one of these equations up here. So which one has a C and D? It's there, it's also there, and then this is the same thing because the order doesn't matter for ands. So I see them in all three equations, so now I have to think, which one can I use? So I'm looking for C and D. In order to use the equation, you have to know everything else in the equation, right? So let's see if one works. I'm looking for C and D, so I need to know these three things. Do I know probability of D? Yes. Do I know probability of C? Yes. Do I know probability of C or D? Also yes, right? So I actually have everything I need for equation 1. So that means equation 1 is the one you want. So I'm going to rewrite equation 1. Let me write it. Yeah, I'll write it here. And then go through and fill in what you know. Okay, so C or D, so this entire thing, I do know. I do know it's 0.92. So that entire thing is 0.92. Probability of C, I do know the entire thing is 0.8. Probability of D, I know it's 0.6. And then probability of C and D, that's actually what I'm looking for. So let me label that with an X. And then I'm going to go through and fill in the symbols. There's an equals here. Between the 0.8, 0.6, there's a plus. And then between the 0.6 and the X, there's a minus. And then your job is to get the X by itself. Okay, so let me first simplify both sides. Left side, there's nothing to do. Right side, I can add those. So 0.8 plus 0.6 is 1.4. And then I still have this minus X. And then I want to get the X by itself. So to get rid of this 1.4, right, currently it's basically being added to this minus X. So I need to subtract both sides. Left side 0.92 minus 1.4 is negative 0.48. On the right side, 1.4 minus 1.4 is going to cancel out, and then I have a minus X. I'm looking for regular X, so if I know negative X is negative 0.48, I know regular X should be positive 0.48. Okay, so what we just found was X, which is probability of C and D. So I know that probability of C and D is 0.48. And the whole point of finding this was to actually check that left side, right? So this left side I now know is 0.48. And the question is, are they equal? No, right? So they're not equal. So our conclusion is that they are not mutually exclusive. Part B. So I'll do part B over here. Are C and D independent? Okay, so independent. I should be checking this equation. So probability of A equals probability of A given B. Right, so let me rewrite that. And then let me also rewrite it with our letters for this question. So we're using C's and D's. So it's probability of C equals probability of C given D. Okay. Check left side, check right side, and check if they're equal. Left side, probability of C, I know it's 0.8. Okay, right side, C given D, I don't think I have yet anywhere. Okay, so I actually have to find the right side. Okay, so I have to find probability of C given D using one of these equations. All right, so which one is going to be useful to me? All right, so for the givens, the order does matter, so it needs to look exactly like that, C given D in that order. Which equation? I see it right here. All right, so I'm going to use equation 3. So let me rewrite equation 3. So equation 3 is probability of D and C is equal to probability of D times the probability of C given D. And then go through and fill in what you know. D and C. Do I know D and C? Yes, right. D and C, remember for and, the order doesn't matter. So D and C is the same thing as C and D. And C and D, we actually found right here. It's 0.48. Okay, so that's 0.48. Probability of D, we know is 0.6. C given D is what I'm looking for to find this right side. So that's X. Go through, fill in the symbols. There's an equal sign right here. There's a multiplication right there. And then your job is to get the X by itself. Right now, there's a multiplication here. So I need to divide both sides by 0.6 to get rid of it. Left side, 0.48 divided by 0.6 is 0.8. Right side, 0.6 divided by 0.6 cancels out, and I have just an X. So X is by itself, and so that 0.8 was just probability of C given D is 0.8. So now I know that the right side is 0.8. And what's our conclusion? They are equal. Okay, so if they are equal, then our conclusion is that they are independent. Example 4. At a certain college, 80% of all students take statistics and 36% of all students take economics. Given that a student takes statistics, 30% of these students take economics. Part A, let S be the event that a student takes statistics, let E be the event that a student takes economics. summarize in symbols the probabilities described above. So what I'm looking for is things that look like this, or this, or this. Okay? So the first probability here is 80%. So as a decimal, that's a 0.80. Okay, and then 80% of all students take statistics. So that's the probability of getting someone who takes statistics. So probability of S. The second percentage here is 36%. As a decimal, that's 0.36. And this represents the percent of students who take economics. So that's going to be probability of E for economics. The last percentage here is 30%, which is 0.30. And this stands for, given that a student takes statistics, 30% of these students take economics. So keyword here is the word given. So this is going to be a conditional probability. So in symbols, it's going to be something given something else, right? So the question is it S given E, or is it E given S? So the way the sentence is written here is that it says, given that a student takes statistics. So that's the given part, right? So given statistics, so given S. And where does the given part go? The first part or the second part? The given is the second part in the symbol. So that means that S goes in the second part, which means E goes in the first part. So this is E given S is 0.30. Okay, and then from here, we're going to need those three formulas. So I'm going to write out those three formulas. I'm going to write them using S's and E's. Okay, so the first one is the addition rule, which is S or E is equal to P of S plus P of E minus P of S and E. The second one is the multiplication rule for ands, so S and E is equal to probability of S times the probability of, and then it alternates, so it's S and then E given S. And then the third one you get by just swapping the S and E's in equation 2. So that's E and S is equal to probability of E times the probability of S given E. And then once again, it alternates, so E and then S given E. Part B, find the probability that a randomly selected student does not take economics. So keyword here is not. I'm looking for a probability of not E, not economics. Okay, if I know E is 0.36, not E, right, so that's the complement, we just do 1 minus. So probability of not E is 1 minus the probability of regular E, and that's 1 minus 0.36. 1 minus 0.36 is 0.64. Part C, find the probability that a random selected student takes statistics and takes economics. Keyword here is and. So in symbols, I'm looking for probability of S and E. And the question is, which equation are you going to use? So I have S and E in actually all three equations. So I have it here, I have it here, and then remember for ands, the order does not matter. So E and S is the same thing as S and E. So it's in equation 3 also. So which one do you use? Remember, in order to use an equation, right, you have to know everything else. So in equation 1, I'm looking for S and E. In order for equation 1 to be useful, I need to know the other three things. So do I know S or E? I don't. Okay, so I can't use equation 1. What about equation 2? So I'm looking for S and E, which means I should know the other two things. Do I know P of S? Yes. Do I know P of S given E? I mean, probably of E given S? Yes. Okay, so I do know the other two things, which means equation 2 is going to be useful. So let me rewrite it. So probably S and E is equal to probability S times the probability of E given S. And then fill in the things that you know. S and E, that's what I'm looking for. So let's call that X. Probability of S, 0.80. Probability of E given S, 0.30. And then fill in the symbols. Right here is an equals. Right here is a multiplication. And then get the X by itself. So right now the X is already by itself. So all you need to do is do the right side. 0.80 times 0.30. 0.24. Right, so what we found was X, and X was the AND. So our answer here is S and E is equal to 0.24. Okay, part D, find a probability that a randomly selected student takes statistics or economics. So keyword here is or. I'm looking for probability of S or E. Okay, which equation should I use? There's actually only one equation that has an or in it. And so I have to use equation 1. So let me rewrite it. That is P of S plus P of E minus P of S and E. Okay, fill in the things that you know. Probability of S or E, that's what I'm looking for. So let me call that X. Probability of S, 0.80. Probability of E, 0.36. Probability of S and E. It's not one of these, but we did actually find it in part C, right? S and E is 0.24, so that's 0.24. Go through, fill in the symbols. There's an equals here. Be careful with the symbols. There's a plus here. There's a minus here. And then get the X by itself. The X is already by itself, so all you need to do is do the right side. And it's 0.80 plus 0.36 minus 0.24. And you get 0.92. Okay, so what we found was the or. So probability of S or E is 0.92. Ran out of ink there. Part E, find a probability that a randomly selected student takes statistics given that the student takes economics. I see the keyword given. What I'm looking for here is something given something. Question is it S given E or is it E given S? It's statistics given economics. So it's S given E. All right, let's look at our formulas. Which one has S given E? And remember, conditional probability, the givens, the order does matter, so I do want it as S given E, exactly like that. I see it right here. All right, so I'm going to be using equation 3. Let me recopy it. Equation 3 says probability of E and S equals probability of E times the probability of S given E. Go through, fill in what you know. E and S. For ANDs, the order does not matter, so E and S is the same thing as S and E, which we did find already in part C, and it was 0.24, so that's 0.24. E, probability of E, 0.36. S given E, that's what I'm looking for. Let's call that X. Go through, fill in the symbols. There's an equals here. There's a times here. And then your job is to get the X by itself. Right now, there's a multiplication there, so to get rid of that 0.36, you're going to do the opposite, which is divide by 0.36. Okay, left side, 0.24 divided by 0.36. And then round it to 3 decimal places, that's 0.667. Right side, 3636 cancels out, and you have just an x, and you're done. So what we're looking for was this probability of S given E, and we found that it was 0.667. Part F, determine if the events taken statistics and taken economics are independent, right? So to check independent, which equation should I be checking? You have two choices. You have this one or this one. We're checking independent, so we're checking probability of A equals probability of A given B. And then let's rewrite this using the letters in this problem. So we're talking about S's and E's. So this is probability of S equals probability of S given E. Okay, find the left side, find the right side, and then see if they're equal. Probability of S, I do know from the beginning, is 0.80. S given E, do I have that somewhere? I do, I have it right here. So that's 0.667. And then our conclusion, they're not equal. So they're not independent. Part G, determine if the events taken statistics and taken economics are mutually exclusive. So here we're checking this equation. So let me rewrite that with S's and E's here. So we're looking for probability of S and E equals 0. Check left side, check right side. Right side's easy, it's 0. Left side, S and E. We probably did that somewhere already. S and E is right here in part C. It's 0.24. Our conclusion, they're definitely not equal, which means they are not mutually exclusive. Have a good day, and I will see you in the next one.